lecture, we'll discuss visualizing data in R and some basics of creating data summaries. This presentation will give you a background on best practices for graphical analysis, teach you to plot data in R, and also summarize data using the dplyr package for purposes of graphical presentation. Some good practices you should keep in mind include ensuring that legends and titles are both clear and accurate, ensuring that plots can be printed in monochrome, and include a combination of different symbols and line types in your plots to allow clear communication of data. It is imperative that when you select axes types, they best and accurately reflect the actual data. Let's take a look at a more complex dataset next. This dataset comprises of data from a single ascending dose study in which a single IV bolus of 50, 100, or 150 milligrams was given to 6 subjects at each dose level. PK concentration samples were collected up to 12 hours post-dose, and the lower limit of quantification of the bioanalytical assay was 1 nanogram per ml. Before we start, I want to emphasize the importance of writing clear code that can be revisited by yourself or another person months or years later. The pound sign allows you to add comments to the R code, and any text after the pound sign will be ignored. This allows us to annotate the R code with what we're doing, and it's good practice to make sure you annotate the R code well to allow others to easily review and reproduce the work conducted. It's also good practice to keep annotations for personal use, as it becomes difficult to remember why you performed a certain manipulation months or years after the fact. I have found annotating code also helps for future instances where you may want to reuse that particular code for another project. We will expect for homeworks that the R code is well annotated and easily interpreted. We will start, as always, by reading in our data. And I want to introduce you to a method which will help to keep the R code clean and presentable in case we have a long file path. We can assign the path of our file to an object. Let's say we call it data path. The entire path should be in parentheses and the folders separated by 2 forward slashes. And ensure that either data path ends with 2 forward slashes or that you add a file name to be read with 2 forward slashes to start. To read the CSV file, we need to join the file path with our file name using paste 0. Paste 0 joins the 2 names without any spaces between them. Paste will join the data path and file name, but there will be a single space between the 2. We can next read in the file assigned to object pk002, equal to using the back arrow, read.csv followed by paste 0 of data path and pk002 underscore example.csv in parentheses. If we head the object pk002, we can see the first 5 rows of data and column names. You could similarly use the function tail to see the last 5 rows of the dataset. We can see that we chose the names of our columns well in the dataset. There are no special characters and all text is capitalized, which simplifies things for us. As mentioned, it's best to avoid using any special characters in the naming of columns in the original datasets where possible, as they do not import the exact same way into R. I would suggest using no spaces, and where spaces are needed, separating words with an underscore, as well as avoiding punctuation such as periods, parentheses, forward and backslashes, etc. Since this example is an IV bolus, we don't want to plot pre-dose concentration, So we will subset our data to remove pre-dose. The presentation on subsetting data goes into more depth on how to subset datasets. However, here we will take PK002 dataset. The first argument tells R which rows to include, and the second tells R the columns to include. If they are all blank, all rows or all columns will be included from the dataset. The first statement tells R to include all rows where time does not equal pre-dose. The second argument is blank and thus includes all columns. Let's head up PK002 and see if the pre-dose values are now removed. I'd like to take a look at the concentration column now, and we can do so by calling PK002 $concentration. PK002 refers to our dataset, and $concentration points to the concentration column within that dataset. We can see that there are some concentration values which are LLOQ and reported as character type data. This immediately tells us that the concentration data is a mixture of character and numeric data, and as such, the column will be considered as character by R. For our analyses, we would like to consider concentrations that are BLQ, below the limit of quantification, as 0 nanograms per mil. We can do this by using the function if-else. If concentration equals LLOQ, then 0, else the value of concentration. Now, if we call the transformed concentration data column, we can see that the less than LLOQ samples are replaced by zeros. We will start by creating a simple plot using the plot function. The first argument in the plot function calls for the x variable, and the second calls for the y variable. In this case, the x variable is the time column of PK002, and the y variable is the concentration column of PK002 dataset. Resulting in this plot, let's say we want to add some more detail. For example, a more clear X and Y label. We can specify the labels for X and Y axis using either XLab or YLab. And here we're specifying that the X-axis label as time in hours and the Y-axis label as concentration in nanograms per mil. We can switch between windows by going to Windows and clicking on the graphics device. We have a more clearly labeled plot now. We can also add special characters such as superscript or Greek letters, etc. We can take a look at the cheat sheet for further information. We can set the y-axis to log scale using log equals y, with y being in parentheses. And we can see that the plot is transformed to a log y scale. Say we want to place two plots side by side. We can use the function par mfrow argument that sets the number of rows to 1 and columns to 2. So the plots will present side by side. If we want one plot on top of the other, we can use mfrow equal to 2, 1, and so on. The first argument refers to the rows, the number of rows required, and the second refers to the number of columns. After setting the option for number of plots per window and how they will be laid out, we can plot our data. The first plot is concentration versus time on a linear y-axis, and the second set is concentration on a log axis versus time. The linear plot will be laid out on the left and the log plot on the right. Once par is set in this manner, all other plots in the graphics window will be plotted with 2 plots on each window. To close out of this option, you can exit from the graphics window when you're done, and new plots will simply open up in a new graphics window. Alternatively, you could always reset par to whatever you need for the remaining plots. Close out of the window, or as I mentioned, the next plots will also have the same layout and as specified. One thing to note is that we had 3 dose levels, but based on this plot, we're not able to distinguish the different dose levels. We can subset and plot each dose individually though. As a note, the minimum and maximum values of the x and y axis can be altered using xlim equals c and the range min and maximum within parentheses. The same can be done for the y lim using the y-axis. We can start by subsetting the 50 mg dose level. With the PK00 dataset, all rows where dose equals 50 will be selected, and all columns. The same subsetting structure can be used for the 100 and 150 mg dose levels. We will first create a plot of the highest dose level, 150 mg, using the function plot. The first argument is setting the x variable, time, and the second argument sets the y variable, concentration. The label for the x-axis is set using xlab equal to time, and ylab sets the label on the y-axis to concentration. It is possible to add subscripts and Greek letters to the label using expression and paste functions. And here is the plot generated of concentration versus time. Next, to add the 50 mg and 100 mg dose levels, we can use the function points to overlay data from the 50 and 100 mg dose levels. Note that we can specify the color using COL equals. Other low-level graphics functions can be specified include the symbol type using PCH, specifying whether we have points, lines, or both for plot type using TYP equals, X and Y limits using xlim and ylim. The details of the additional low-level functions can be found in the tip sheet. And here is the plot. We can see that the different dose levels are plotted in different colors, black, purple, and blue. We can use the function legend to add legend to the plot. The first argument specifies the x coordinates, and the second specifies the y coordinates. PCH equals 1 specifies the symbol type will be open for all, and col will specify the color of the symbols. Legend equals will add text to the legend. So now we can see the legend was added, and there are various other options such as including or removing the box surrounding the legend, spacing between the symbol and text that can be updated, and further details of these can be found on the tip sheet. Instead of a scatter plot, say we want to create a spaghetti plot with lines connecting the concentration values within a subject's PK profile. Let's consider changing the type of plot to TYP equals B. We created a plot with both symbols and lines. However, one thing to note is that R was not able to understand that each subject's profile is separate, and therefore they are connected. There are a number of ways we can work around this, for example using loops or other packages. Let's take a look at the Lattice package further. First of all, you will need to ensure that Lattice was installed. Next, load up Lattice using the require function. XYPlot is a function in R, Lattice, used to create a simple plot. Other types of plots can be called using other functions in the tip sheet. The first argument is the Y variable, followed by tilde and the X variable. The majority of low-level functions to update the graphics labels, etc. are similar to a standard plot. Auto.key set to true will automatically generate a legend, but some more details on tailoring the legend in Lattice will be discussed later. Now we will create a Lattice plot with our example data. Using the XY function, we will plot Y concentration by X time. We will group profiles by subject and create a plot with points and lines connected using TYP equals B. And finally, we want to plot the Y-axis on a log scale. We do this using the scales argument. We can see the plot side by side with the code, and we can see that we created a concentration versus time plot stratified by individual subjects. We could tidy this plot up a bit further by updating the X and Y axis labels and adding a legend. As mentioned earlier, setting auto.key to true will provide a basic legend, as we see here. To tidy it up a bit more, we can specify the location and title for the legend. Using auto.key equals list, we can specify the space to be on the right-hand side of the plot and the legend title as subject. We can also split plots by study cohort using pipe and cohort. This creates 3 plots. But the headers are not clear, and that is because Lattice stratifies by factors and our data are numeric. If we force cohort data to behave as factors using as.factors, we are able to label each plot more appropriately with the cohort number. Now let's take a look at the dplyr package. dplyr is a package that can be used to summarize and reshape data from data frames. In particular, it can help us to summarize data by creating groups of data and calculating means. We can transform columns of data using mutate to create new columns. This could be useful in the case of handling concentration that are BLQ or time data which include both non-numeric and numeric values. We can select out certain columns and also filter data efficiently. We will focus on using dplyr to group and summarize data. However, dplyr is a very powerful tool that can be used for data manipulation and handling, and I encourage you to read further into this package and use inbuilt examples from our data sets and become more familiar with this package. First, load dplyr using the require function. We can see that dplyr package was loaded successfully. dplyr uses a piping to state that with pk002, do this. On the right side, the function is grouped by cohort and time, and with the grouped values summarize to concentration equals mean of the concentration values. This will provide a mean concentration for each cohort at each time point. Now, if we type in mean, we will see the summary statistics that were generated. Let's quickly rename the columns to something more manageable. Names of the mean dataset will be cohort, time, and conc. Now call out mean and we see the column names were updated. We will now take the summarized data and create plots of mean concentration versus time, stratified by cohort. We will create a plot with both points and lines using TYP equals B and on a log Y scale using the scales option. And we will update the Y and X axis labels to concentration in nanogram per mil and time in hours respectively. Additionally, we will use the auto.key function to specify the legend will be placed on the right of the plot and titled cohort. We can see that the plot was generated successfully. Lattice is a great package that allows you to visualize data and has many potential visualizations and a variety of plot types. I would encourage you to read over and become familiar with the options in Lattice from the reference material. Additionally, other packages such as ggplot, plotly, and many others can provide numerous options for graphical analysis. And while it's beyond the scope of this class to go through each of these packages, it's worth being aware of them and looking into them further. Visualization of bioanalytical data facilitates review and is a quick method to note anomalies that need to be further queried. You should be able to create basic plots in R and use Lattice to further stratify plots. You have been introduced to the package dplyr, and you will be able to use this package to summarize data for further graphical analysis. Since dplyr is a powerful tool for data frame manipulation, it can be used for a number of other functions such as filtering data, selecting columns, transforming data using mutate, and reshaping data frames. This introduction to R will give you a good place to get started in importing datasets, reviewing and creating graphs, but there are many more possibilities, and I would encourage you to read further into this during and after the PK course.